Right. Hello class, this is CSE-5250, sections 2 and 60, week 3, spring 2025. Right, so for both CSE-5250, sections 2 and 60, you now have online portions to the entire course now. So, in the first half of our discussion on Pthreads, we began with a simple Hello World program. Our next part is to consider writing a program that has a critical section. So the idea is simple. If we have multiple threads trying to access the same resource, we have the danger of getting a race condition. So let's start out with writing a preliminary program that has a race condition in it that we're gonna resolve step by step. Okay. So for that, we're gonna begin with a program that is going to be used to calculate the number pi based on a summation. So this is the formula here. It's 4 times this infinite sum here. So 1 minus 1/3 plus 1/5 plus... No, 1... Okay, so it's 4 times this summation here. So 1 minus 1/3 plus 1/5 minus 1/7, so on and so forth, where the nth term in this sum is negative 1 to the nth power times 1 over 2n plus 1. We can realize this in code that looks like this. So we're going to have a factor that we're going to alternate from being positive and negative. We have a sum that's going to contain the sum of all our variables, no, all our terms. And then we have a for loop that we're going to run for n iterations. So let's say we're adding 1,000 terms. This for loop's going to run for 1,000 for loop iterations. So if we had p threads, we would give n over p loop iterations to each thread. Here, the sum becomes a global variable where each thread must access it to, well, calculate the number for pi. Alright, so let's begin writing those instructions right now. Okay, so here are the instructions for your first lab. Well, lab 1, we have a lab 0. So we're going to start off by writing a simple single-threaded pi estimating program. The point values are all wrong. My bad. So this is actually 15 points. And this other one is actually 20 points. So there we go. Oh, okay, there we go. All fixed up. So we're going to begin by writing a single-threaded pi estimating program just to get our feet wet, okay? Give me a minute. Okay, so I've just created a brand new, here I've created a brand new folder on my Linux VM. Oh, by the way, this is the kind of lab for which we are going to be needing a Unix system. So if you're on a Mac, you're good to go. If you're on a Linux system, you're good to go too. If you're otherwise able to access either of those, you're also good to go. But if you want to do this on your Windows machine, you need to set up a virtual machine. Okay. So let's enter this folder here and let's open the terminal at this location, and we're gonna create a new program. Let's call it pi.c. But I need to create a source code file. So pi.c. This is just gonna open up VI. What I'm going to do is press escape, type in WQ. This saves the file, and that way we have a new file. You can use VI to type your code. There are other text editors like this that we're going to terminal, but I personally like to use a text editor like this. So let's quickly write up a program that estimates the value of pi. So we're gonna let's think about this and okay, so I'm just gonna put in standard io.h because I'm gonna need to do like a printf operation. So let's do this. Int main and we can just make it pretty basic. So int terms equals, let's begin with 100 terms and see how this is gonna run. I'll write a simple for loop for int I equals 1, no, equals 0, I bet. I is less than terms I plus plus. And then, oh yeah, I need a sum. So int sum equals 0. My bad, that should be a double because we're dealing with a floating point thing here. What we could do also is add a factor. So double factor equals 1. And now let's begin by programming in this for loop here. Okay, so I plus plus comma factor equals negative factor. Okay. Now we can simply write in sum plus equals factor divided by 2 times I plus 1. After that, we can simply print out our value for pi. So double pi equals 4 times sum and print f There we go. Alright, for us to compile this, there is nothing about this lab that requires any Pthreads or at all, or the like, so we can just say gcc-o pi.c. Okay. There is a conversion problem here, so I believe that should be %f, not %d, because this is a floating point value. So let's try that again. And okay, so estimated value of pi using 100 terms in our sum is 3.131593. Not quite right. It's 3.14159, so on and so forth. But so let's try a different number of terms. Let's try 100,000. So we're gonna try that out, and we need to recompile our program. So recompile /pi 3.1411583. Still not quite right, but a little bit better. See, we got our program working. Okay, let's make a multi-threaded variant of this program. Let's call it Pthreads. So vi pi threads.c. I'll just press escape :wq to create a new file here. There we go. So here's where it starts to become a little bit complex here. So you're gonna have to give me a minute. Okay, so the instructions are also in the slides itself. So I'll be posting this on Canvas if it isn't posted there already. So we're gonna begin with our boilerplate code. So include standard i.h include standard library.h include pthread.h. There we go. We're gonna need a few global variables. So those are int thread count. We are adapting some of this from our previous Hello World program. So this is the global variable for the number of threads we have, int n for the number of terms we're adding, and double sum. We'll initially set that to 0.0. So this is gonna be the sum that we're calculating. We're also gonna need a function footer type void star thread sum void star range. Okay. The next thing we write is our main function. So it is much like the previous lab 0. We have this thread function take in command line argument. So int main int argc comma character star argv square brackets. Let me just populate this function here. So return 0 at the end, and then let's begin. We need a 64-bit integer, so for our purposes we're gonna use long for this. This is technically not correct because in some cases what we think is we think of a long as being 64 bits wide, but that might not be the case on some systems. There is an unambiguous equivalent to this, which is exactly 64 bits because, yeah, some platforms are a little bit different. But so just in case this doesn't work, you're gonna have to look into what that unambiguous data type is. So, but for now, we're just gonna use long thread, and then we need a pointer for our thread handle. So p thread underscore t star thread handles. Next, we're gonna get the number of threads and number of terms from the command line. So previously in our lab 0, we had the program take in the number of threads to run. Here we're gonna do that for both the number of threads and the number of terms. So argv1 is the number of threads, argv2 is the number of terms. So thread count equals strtoll argv1 comma null comma 10 because it's base 10, and then n equals strtoll argv2 null 10. There we go. Now we get to allocate memory for our thread handles. So thread handles equals malloc thread count times size of pthread t. It would be a good idea to comment this thread so we know what we're looking at, so give me a minute. Okay, there we go. Okay, so we allocate memory for our threads, and then we call pthread create within a for loop. So for thread equals 0, thread is less than thread count, thread plus plus, and within this for loop, I'm gonna call pthread create. Pthread create, pass in the address of a thread handle, pass in null, pass in the thread sum function here, and finally void star thread. This is just so we can get the thread ID. There we go. Once those threads are running, we can join back with the main thread. For thread, I'll just copy this line of code here. Copy, paste. So thread equals 0, thread less than thread count, thread plus plus. We're gonna call pthread join. We're gonna pass in a thread handle. And then we're gonna pass in null because we're not returning anything from this function. When we're done, we're gonna deallocate memory. So free. There we go. We got thread handles and return 0. The final step is our thread sum function. So we're gonna say void star thread sum void star rank. It's gonna return null. There we go. And then we're gonna add a few variables here. So this is gonna be long my rank equals. We're gonna cast this parameter here to long. So long rank double factor. So this is the factor that was from here that flip-flops from positive to negative. We're gonna say long I long I n equals n divided by thread count. There we go. Then I'm gonna say long my first I equals my n times my rank. So basically, if we have, say, 10 threads and 1,000 for loop iterations, the first thread gets the first 100 loop iterations, the next thread gets the next 100 loop iterations after that, and the next thread gets the next 100 loop iterations after that, and so on. But don't think of these as loop iterations. Well, they are loop iterations, but they are also terms in our summation. So the first thread adds the first 100 terms. The next thread adds the next 100 terms after that. The next thread adds the next 100 terms after that. Okay? Alright. Is that everything? Okay, so for this for loop to work, we need to calculate the starting and ending position for each for the portion of terms that each thread is calculating. So long my last I equals my first I plus my n. So for example, if we have 10 threads and 1,000 terms, the first thread 0, is adding terms numbered 0 to 99. Thread 1 adds terms numbered from 1 to 199. Thread 2 adds terms from 200 to 299, and so on. We need also this. If my first I is divisible by 2, and a divisibility by 2 check is simply divide by 2 and check whether the remainder is 0. So that would be my first I mod 2. Is this equal to 0? If so, factor equals 1.0. Otherwise, else, factor equals negative 1.0. Oh, we don't need the F. Okay, and now we can get to our for loop. So for I equals my first I is less than my last I is less than, no, I plus plus, comma, factor equals negative factor. And then sum plus equals factor divided by 2 times I plus 1. And there we go. So when we run this program, make sure you type in a number of threads and a number of terms, or else we're going to get a seg fault. Also, there is a little bit of a bug in this program. If we are dividing our summation amongst a number of threads that isn't divisible by the number of terms, so if we, for example, try to add 101 terms between 10 threads, there's an extra term that might not be accounted for. because 101 does not divide cleanly by 10. There's going to be a remainder of 1. That one extra term, that's a remainder 1. It's going to go missing. We're going to write some code that'll fix that up in our next step. No, that's our next assignment, actually. The next step is actually a debugging session for this program. So we're going to assume that the number of terms we're adding is divisible by the number of threads we're using. So let's save the program, and we're going to compile it by saying, okay, so the compile command is a little bit longer here, but it is in one of the first slides of the presentation. So gcc-g-wall file name without the file extension, so that was Pthreads threads.c because that's the source code file, and then dash lp thread. Okay. Updates. Remind me later. Okay, so there is a bug I have to fix here. That was on line 32. That was thread handles plural. Let's try it again. Cannot find Pthreads, no such file or directory. I guess maybe I mistyped it. Yeah, I did. So it was gcc-g-wall- oh! There we go. If we do /Pthreads, it just defaulted because they didn't pass any arguments. If I instead say /Pthreads, and then I say, okay, so the first the first argument is the number of threads. So, and the next argument after that is the number of terms. I'm gonna try 10 threads and 1,000 terms. Oh, you know what happened? I forgot to print out the result. So I'll just copy that and paste it into here. Actually, I'll just yeah. So there we go. Let's try this again. 3.140593, and if I run it again, and again, and again. Okay, it's working. Perfect. So what we want to do now is see whether there are any issues with their code. And spoiler, there are issues. They were just not manifesting themselves just yet. But if I do something like this, if I say do 100,000 terms spread amongst 10 threads, then what will happen is this. I am calculating the number pi, but hey, look, the value of pi is changing every time we run a program. That's the race condition that's happening. And if I do this again, but with a different number of threads, say 1,000 threads and 100,000 terms, yeah, so now our value for pi is changing every time we calculate it, and that's because of those race conditions. So what's happening is the problem of race conditions. So if we have, say, the number 30 stored in a shared variable that two threads are trying to access, what should happen here? One thread is trying to add 3 to that stored variable. Another thread is trying to add 5 to the same stored variable. We should get the number 38, but the problem is this can happen out of sequence. So if both threads try to add to the same value at the same time, they'll grab the number 30. Both of them will grab the number 30. One calculates 30 plus 3 equals 33. The other calculates 30 plus 5 equals 35. And then they try to store them in their answers in the same slot. So it's gonna be either 33 or 35, depending on who writes their answer last. Last place wins because that's the answer that's last. The answer that's last is the one that lasts. A bit of wordplay there. So yeah, we have a critical section that we have to account for, but I'm gonna save that for when we talk about our next set of slides, so that's gonna be for next week. So, we're gonna continue on with this lab next week. We're gonna have some more new material, so your next slide is gonna be resolving these issues. So taking this code that we wrote here and fixing up the bugs, so we don't have the issue of race conditions. So what's going on is the variable called sum is a global variable, and we are having the problem that I just described where two threads are trying to add to the same variable at the same time. What we need to do is declare this section of code a critical section, so only one thread at a time can access it. Alright? So that's gonna be what we're gonna fix up next week. So yeah. So the idea is we fix this up and we get our code up and running again. So there are a few pitfalls with trying to enforce mutual exclusion, as it's called, that we're also going to explore next week as well. Alright? Okay. So this is going to be your next assignment for both CSE-5250 sections 2 and 60. Okay? Alright. If you have any questions, let me know. And for now, I'll be posting all of this as soon as possible, so you can get to work as soon as possible. Okay? Alright. Take care, and see you next week.